In this section, we'll discuss solar electric modules. This solar array on a health clinic consists of several solar electric modules. You may also be able to pick out the individual cells inside each black-framed module. So, what is a PV module? So a PV module is a group of photovoltaic cells that are wired together for greater voltage or current or both and put in a mechanical package. So commercial modules, like the ones we saw on the last slide, usually have protective glass on the front with special anti-reflective coatings, a weatherproof coating on the back, and an aluminum frame. We can also wire multiple modules together to form an array, as we saw in the photograph on the previous slide, a grouping of solar electric modules. There are several different technologies used to build solar modules. These include monocrystalline, which have the highest efficiency, polycrystalline, which have a slightly lower efficiency, and thin film technologies, which are significantly less efficient than crystalline technologies. Of course, efficiency isn't everything. What's really most important is the cost of energy for the module over time. One commonly used measure for purchase is dollars per watt or cost per watt, though this does not tell the whole story of reduction over time. Most small-scale projects, we use one of the two crystalline technologies due to their availability, performance, and cost. And either monocrystalline or polycrystalline is fine. In most cases, their performance is very similar. To understand how much energy we can get from a solar module, the first place to start is the manufacturer's datasheet. This document can give us most of the relevant information. On the sheet, you might find what's called an IV curve, as shown on this slide. This graph will show you performance numbers for a module at various voltages and currents. For example, where the curve labeled 1000 watts per meter squared intersects the y-axis on the left, there's a quantity that's called short circuit current. On the lower right, the intersection with the x-axis is called open circuit voltage. We'll discuss both these quantities in the next slide. For maximum energy harvest, we want to operate somewhere between the extremes. Many factors affect energy output, such as sunlight intensity, shading, cell temperature, and load characteristics. If you don't see an IV curve on the datasheet, don't worry. You can get much of the same information from the tables. First, we have maximum power. This value is the maximum power that you'll get from a module under specific test conditions. By the way, these test conditions don't often occur in the real world, so output is usually less. So this is sometimes just called Pmax. The maximum power value occurs at a specific point on the IV curve. This is the intersection of the maximum power voltage, VMP, and the maximum power current, IMP. This is what we call the corner of the IV curve at the upper right, if you recall from the last slide. As mentioned on that last slide, open circuit voltage is an important quantity. This is the voltage the module will output when it's put in the sun and not connected to any load. You'll hear this called simply VOC for volts open circuit. On the other end of the IV curve, we have short circuit current at the lower right. This is the current in amps that a module will output if we short circuit the module leads together in full sun. This is often referred to as ISC, since I is commonly used to mean amps and SC for short circuit. It's worth noting that photovoltaic modules are one of the few electrical devices that you can short with absolutely no ill effects to the module. Although VOC and ISC are important design parameters, operation at these values won't produce useful energy. So we want to be, again, somewhere between the two, ideally at that maximum power voltage to yield our Pmax output. So I know this is a lot of information to digest, so I would recommend you take some time to do additional reading on this topic if any of it's confusing, and to especially learn more about any electrical terms that you are unfamiliar with. In this section, we looked at solar modules in detail. In the next section, we'll look at wiring, overcurrent protection, and disconnects. In this section, we'll talk about wiring, overcurrent protection, and disconnects. Although these three areas are sometimes left as an afterthought in system design, a large number of system failures happen because of poor design or installation in these areas. In addition, overcurrent protection and disconnects are key safety features which help keep people and property safe.